Hello students, welcome back. Let us resume our discussion in section 7. We just discussed linear Diophantine equation, the general form versus the standard form. So this equation, ax plus by equal to c, has no integer solution if the GCD of the coefficient a and b does not divide c, and it has infinite many solutions if that GCD divides c. Not only that, you can have appropriate reduction. Suppose that we have this, and also D is GCD of A and B. Suppose that we have this, then what conclusion can we draw? Divide everything by D, then I'm gonna get A over D x plus B over D y is equal to C over D. Now, A over D, is that an integer? Yes, indeed, no problem there, because D is a common divisor. B over D, is that an integer? Yes, indeed, because D is a common divisor. How about C over D, is that an integer? Not in general, but we have an additional condition here. In this case, it breaks down. In this case, it works. Moreover, in this case, sorry about the typo, the GCD of these two integers, A over D and then B over D, is 1. Remember this, by the way? Divide by GCD and we have 1. Remember this? We went through that in lesson 7 somewhere. Right here. And here's a hint for the proof. As a matter of fact, here's a full proof. Remember that? Okay, so we are there. And then let us rename those. A over D, say alpha, and B over D, say beta, and C over D, gamma. We get that. And then GCD of alpha and beta is 1. So through this arrangement, we come down to the standard case. We went through an example already. In this kind of problem, divide each by the GCD, which is 10. So divide by 10, divide by 10, and divide by 10. We are at the standard place. In this case, the GCD is 3, and 3 does not divide 83, so we can't do it. But let's suppose that we have something different. Instead of this is 83, what if we had 81? In that case, we can divide each by 3, and you're gonna get what? 2x, 5y, and then divide by 3, I'm gonna get 27. Yeah, okay. And then we are into the standard case. So let's consider the standard case first. So if D divides C, we can bring it down to the standard case where GCD of A and B is 1, so they are relatively prime. In that case, I don't really have to worry too much about this thing divisible by GCD because 1 divides everything, and it's been already checked, by the way. And this one has infinite many solutions, but not only that, of this form. So ax0 plus by0 equals to 1. We could find such x0 and y0 because a and b are relatively prime. Remember Bezout's linear combination expression? And how do you find this linear combination? We use the Euclidean algorithm. We went through those kind of example problems before, like this. Euclidean algorithm, and then find D, and then we backtrace to get those linear combination expression. Remember that? So we can find x0 and y0. Moreover, the general solution looks like this. Cx0 plus bt, cy0 minus at. So what we have, not only we can prove that there are infinite many solutions because t can be arbitrary integer, but also we have the general formula. Find x0, y0 through Euclidean algorithm. Okay, that's step 1, and that can be a bit significant. A lot of steps. And then step 2. Step 2 is actually easy. Just a formula, and there it is. Okay, how do you prove it? Let's begin. First, a preparation. You can always find x0 and y0 like this. And you can use Euclidean algorithm for that. All right, now the easier half. Start from the right-hand side, and let's prove that such x and y satisfy the original equation, the standard case. There you go. Define x as this, and define y as that, as you have in the right-hand side, where t is arbitrary. And then plug those into the original equation, and do some algebraic manipulation. Please check. It's not too bad. That's your x, and that's your y. As you see from here, that's your x, that's your y, and then x0, y0 part. AC, x0, BC, y0. So take C out. What do you have? You have this thing is equal to 1. Linear combination expression turning out to be 1. And then what you have here, ABT minus ABT. So A times BT minus B times AT. So that whole thing becomes 0. And we end up with C times 1 plus 0, that's C. So we have the solution. That's the easy half. Start from the right-hand side and then plug in and then do some algebraic manipulation. And those are obvious and trivial. Okay, I wouldn't say trivial, excuse me. Obvious was too strong either. Well, those are easy. Now, let's consider a little bit more difficult step. The forward direction. There's no other form. Suppose that we have an answer like this, then they must be of this form for some t. How do you prove that? Let's make a subtraction. After all, we want to prove that this blue and that green are the only types of solution. So in order to prove that, flip this to the other side and flip that to the other side, and we're going to consider x minus cx0 and y minus cy0. So x minus cx0, y minus cy0. And then let's manipulate a little bit, and we can prove that this thing satisfies the equation where the right-hand side is 0. Let's check. ax plus by, okay, we get that. And then acx0 minus bcx0. So c is common, take those out, and negative out, we have ax0 plus by0, which is 1. Yeah, that's 1. So we have c minus c times 1, so we get 0. All right, this thing equal to 0, does it help? Look at the next step. Flip this to the other side to get this. Does it ring a bell? Still no. Yeah, I don't blame you. It's still hard to see. look at the next step, maybe you can see what is going on and why we are doing this. From here, we conclude that A divides this thing because A times something is the right-hand side. And then B divides this thing because B times something is the left-hand side. Do you see that? And then do you see what's going on here? Why we are doing this? A divides B times that parenthesis. B divides A times that parenthesis. Yes, do you see it? Here, we're going to apply Euclid's lemma. A and B are relative primes, so A have nothing to do with B. A should just divide this thing. Same here. B and A are relative primes, so it has nothing to do with A. B should divide only this one here. So that's the conclusion you get. A divides that parenthesis, B divides this parenthesis. So this parenthesis is some integer times A. That parenthesis is some integer times B. Yeah, this thing is A times S, and that thing is B times T. We have to have two different integers. Each time we use existential quantifier, we have to bring in different character. So some integer times A, some integer is S, some integer times B, that's T. And then let's see, we have to bring those down to just one integer. Can we do that? Bring those back into the original equation here. Let's find some relation between A and B. Let's find some relation between S and T. We ended up with S is negative T. See that? This one here is BT. That one here is AS. After simplification, we get S is negative T. Hence, the conclusion follows. This one here, oops, sorry about that. I didn't copy and paste correctly. Okay, here, this one here is negative AT. So flipping the cy0 and cx0 to the other side, you're going to get the desired solution. cx0 plus bt and cy0 minus at. Used to be plus at, now minus at, because s and t are the same except for the sign. Isn't that what we wanted all along? Yes, indeed. So that concludes the proof. Now, the proof of step 3, even if you cannot reproduce it, it's going to be okay because it was a challenge, you see. Getting this homogeneous equation, something equal to 0, that's not outrageous. That's something we do a lot in linear algebra and differential equations and whenever we have linear equations. But arranging like these and applying Euclid lemma, that was ingenious. So we have the proof of the standard case. The general case looks like we'll have to continue in the next video. Okay.